Welcome to Monday. Welcome to the penultimate lecture of the course. We just have today and Wednesday, and then for the rest of the semester, we just have reviews for exams and exams. And that's all there is to it. So we are very much done. A couple of housekeeping notes. Don't forget that assignment 11 is due today, as is project number 2. So you got a lot on your plate for today. Hopefully you got a lot of that done already. And then I believe assignment number 12 will be due on Friday. Project number 3 is due on the last day of class. Is due on the last day of class, which is December 2nd. So, yeah. Hopefully you're not jam-packing a busy evening for yourself today. Are there any questions, comments, or concerns about anything related to the course before we get started with today's class? Some folks are typing. The date of the final is the Thursday, December the 4th. And just like before, it'll be available all day from like 8 a.m. until midnight. The class that most closely follows this is microcontrollers. I don't remember what the course number for that is. Another course is a senior elective. Our computer architecture class in our department picks up pretty much where we leave off from here as well. So microcontrollers or computer architecture. In the ECE department, our computer architecture class is different than CS's computer architecture class. In the CS department, your architecture class isn't really an architecture class. It's like an assembly language programming class that they call architecture. So, microcontrollers are fun. Or is fun. It's a fun class. I enjoyed it when I took it many moons ago. All right, let's go ahead and dig into this. Today's lesson is a little bit boring, I'm not gonna lie, but it's pretty easy, and we're just gonna work through some examples of doing signal tracing in order to analyze a sequential circuit. Basically, we're just gonna see two examples of sequential circuits, and we're just gonna kind of draw the ones and zeros and work our way through the examples. So just a quick. Yeah, man, it didn't give us a good backdrop. All the ones that produced today were kind of lame. So, all right, just a quick overview. We're going to go through the procedure for analyzing our sequential circuits. We'll talk about our two basic types of sequential circuits, which are Moore circuits and Mealy circuits, and then we'll work out an example of each, and we'll call it good. So, let's take a look at the analysis. It's pretty simple. The first step is just assume an initial state of the flip-flop. So set all the flip-flops to 0 unless otherwise specified. I can't even think of a reason why you wouldn't set all the flip-flops to 0. For the first input in a given sequence, determine the circuit outputs and the flip-flop inputs. Then determine the new set of flip-flop states after the next active clock edge, and then determine the outputs that correspond to the new states. And then you just wash, rinse, and repeat steps 2, 3, and 4 for each input in the given sequence, right? So we're going to have x is equal to a sequence, and we're just going to work our way through each guy in the sequence. Are there any questions about that process? If it doesn't make sense, it'll probably make a lot more sense when we actually put it into practice. So let's first talk about types of clocked sequential. Yep, I'm recording. Let's double check. Let's make sure. Yep, we're recording. All is well. All right, types of clock sequential circuits. There are two types of clock sequential circuits. Well, there's other types, but primarily there are two types. There's a Moore circuit and a Mealy circuit. And the Moore circuit is the output depends only on the present state of the flip-flops. And a Mealy circuit is the output depends on both the present state of the flip-flops and the circuit inputs. So that's the difference. A Moore circuit output is just tied to the flip-flops, and a Mealy circuit, the output is tied to the flip-flops and to the input. So let's take a look now at an example of a more sequential circuit. So this is the circuit we're going to work out. As you can see, it is in fact a more sequential circuit because if I can get the pin to work. Oh, not the laser pointer. That's pretty cool though. The pin, right? So Z here is tied just to B and A, right? Just to the flip-flops. So Z is equal to A XOR B. It's a terrible B. So that makes it a more because X, our input, has no effect on Z, no direct effect. It's not tied to Z directly. So, and we're going to work through this sequence. X equals 0, 1, 1, 0, 1. So let's do that. I'm going to write over here. I'm going to say X is equal to, what was it, 0, 1, 1, 0, 1. 0, 1, 1, 0, 1. So let's go ahead and kind of lay out our table here. We'll say that we've got a value of X, and then let's say a value of dA and a value of dB and an A and a B and a Z. So a lot to unpack. So we've got the input, we've got effectively the next state, we've got the present state, and we've got the output. Oop. Present. Sorry, I realized I'm under my thing here. And then my output. Just like that. So this is the present state. PS. That's the next state. NS. All right. So we initialize everything to 0, which is really all just to say that X is 0, A is 0, and B is 0. But we can still figure out what we've got for dA, dB, and Z. So if we look down here at our input conditions, we had X is 0, A is 0, which means that that's an OR gate, and that's an XOR gate. That means we have 0 or 0 gets us a 0 at dB. For dA, that's a 0 XOR B prime here, right? Since B is 0, B prime is going to be equal to 1. So 0 XOR 1 is going to be 1, which means that dA is equal to 1. And then, of course, we have Z, which is Z is equal to XOR A and B. So it's 0 XOR 0 is going to be 0. So that's our initial sort of start of the universe conditions. Are there any questions about how we kick this off? So now what we're going to do is now work through our sequence. And this is where it gets kind of, boring, as I said. 0, 1, 1, 0, 1. So we're going to work through each of these sort of individually. You know what? I want to give myself a little more room. So I'm going to erase these. I'm also going to erase those. And I'm going to say 0, 1, 1, 0, 1, just to give myself a little more space. All right, so now we're looking at this first line. X is equal to 0. Now, a couple things are going to happen right off the bat, which are A and B are just going to take that new state, right? Since, remember, these are D flip-flops, transparent flip-flops. So, B plus is just equal to dB, right? And A plus is equal to D sub A. That means this will be 1 and 0. And Z is tied to A and B. So Z is the XOR of that. 1 XOR 0 is 1. So there's our output. And now we need to queue up the next state. So for dA, we had x, which is equal to 0, b prime, which is, remember, we're looking here at b. b is equal to 0, so b prime is equal to 1. So 0 XOR 1 is equal to 1. So dA is equal to 1. And let's see, b is a and x, so x is 0, but a is 1. So we have 1 or 0 gets us a 1, which means that dB is equal to 1. And that's the next line. Any questions about that one? All right, so we'll erase and do the next line. So I'll get rid of that, get rid of these guys, get rid of those guys, bring back the pin. All right, so now we're on this next line. X equals 1 now. The values at dA and dB immediately dump over into A and B. So that's our next edge. Z is going to be 1 XOR 1, which will be 0. Now we're looking at dA and dB. So let's go and say our x's were 1 and 1. Okay, and then A is equal to 1. B is equal to 1, which means B prime is equal to 0. So, looking at dA, we have 1 XOR 0 is going to be 1, so we have a 1 at dA. And then here we have a 1 and 1. 1 over 1 is 1, so dB is also equal to 1. Lots of 1s queuing up. All right, now we go to the next one. Signal tracing is one of those things that is not very hard, it's not very complex, but it is extremely tedious. So now we're looking at here at this one. All right, so we got 1 here. Remember, our initial values here are going to dump over, so we have 1 and 1. So Z is going to stay 0. Okay. And then dA and dB, let's take a look. So we got 1 and 1, and we have 1 and 0 gets us 1 and 1. So we're still going to just keep riding with 1s out here. 1 and 1. So nothing really changes. And we go to erase. Let's go to the next one. All right, now we're looking at 0. So just like before, the values dump over, A and B. Now we've got still a 0 at Z. And then we've got dA and dB. So X is 0, A is still 1. X is 0, B prime is 0. So we've got a little bit of a different thing here. So we've got 0 dA. And still 1 at dB, so we got 0 and 1. And then we're ready to do our last step. Which is going to be X is equal to 1. A and B are going to be 0 and 1. So we're going to have a 1 here. And then, let's see, yeah. And then finally, dA and dB are going to be 1 and 0. And then 1 and 0 gives us 1s again on dA and dB. So that gets us 1 and 1. And then, so that's then for that one. And then we need to do one last step, right? Because we need to kind of figure out what's going on next. So if we essentially don't care about this one, we don't care about this one, we don't care about that one. At the end of the sequence, we'll end with 1 and 1 and 0. So, any questions about that? Like I said, not very complex, but a little bit tedious, a lot of it tedious, and probably not the most exciting thing in the universe. All right, well, if there's no questions about that, I'm going to sort of quickly click past these two slides because they just kind of confused people more than they helped in the first lecture. So let's move on and take a look at our Mealy sequential circuit machine. So here's what we're going to use. We're going to use a similar sequence. We're going to use x equals, come on, cooperate. One zero 10101. So we got XB. So notice now that it's a Mealy one. We've got Z as a function of this logic circuit that also includes the input X. And also notice here that we have what are called JK flip-flops. Then the equation here is Q plus is equal to J times Q prime plus K prime and Q. So that means it's it's not one-to-one. It's not like I don't know why I keep trying to do that. It never works. It's not like a D flip-flop where it's just Q is equal to D. Here we actually have kind of a strange equation for what our behavior is going to be. So let's dig into it and just kind of unpack what we've got. So Mealy and Moore are the names of the types of circuits, Liam. Liam asks, are Mealy and Moore the names of the circuits or the techniques? And they are the names of the circuits. Okay, so let's kind of unpack a little bit. We need to have, make sure I'm not right over myself. We're still going to have X. We're still going to have A plus and B plus. Or rather, yeah, except we got it, yeah, it's a little bit different, right? So A plus, B plus, then we have A and B, and then we have Z. So right off the bat, we're going to sort of simplify some stuff. Or actually, let's do this first. Let's say that, so A plus has to equal JA and A prime or KA prime and A. JB, so B plus, is going to be JB and A prime or KB. Oop, I got that backwards. No A's involved. So JB and B prime or KB prime and B. So those are our flip-flop equations for these guys. So let's make our tables here. The first thing we're going to do is sort of initialize everything, where we're going to have X at 0. We really don't have a value for A prime, A plus and B plus. A and B are both going to be 0, which means Z is going to be what? So we've got, so everything is 0, so it's going to be 0 and 1, 0 and 0, 1 and 1, and 0. Means that we've got 0 and 0, 0, which means that Z is equal to 0. All right, so there's the setup. Now, let's see, what was our 1, 0, 1, 0, 1? So 1, 0, 1, 0, 1. And let's go ahead and work through the process. Okay, so there wasn't, let's see. So we had values for A and B. Hold on. Let me make sure I know what I want to do. Okay. So we got to, it's a little bit more complex. So the first thing we got to do is start with X. X is equal to 1, and notice that we have, so we have a 1 at JB, a 1 there, a 1 there, and a 1 at KA. And then JA and KB are both dependent on these AND gates. The other input is B, which is 0. And here we've got A is equal to 0. So we've got KA is 1, JA is 0, KB is 0, and JB is 1. Down here, I'm going to go ahead and use this space to work out my values for AB, or A plus and B plus. Okay, A plus is equal to JA, which was 0, and A prime, which was 0, gives us a 1, or KA, which is 1, but KA prime is equal to 0, and A was equal to 0, so that means that A plus is equal to 0. Wait, hold on. I think I'm kind of confusing myself a little bit. I did it slightly differently this morning, and I thought this would be better, but now it's proving to be worse. Maybe Z. Okay, never mind. Let's keep it going. So let's do B plus is JB and B prime. So that's going to be 1 and B prime. So B was equal to 0, so that's equal to 1. Or KB prime is going to be 1 and B, which is equal to 0, which is going to be 1 or 0, which is going to be 1. So B plus is going to be equal to 1. So here's my question for you guys. Let's work it out. Take a second. Let's figure this out. What are A and B supposed to be on this chart? Because it gets a little loopy, right? There's not a clear sort of tying right there because we didn't have values here. What do you guys think? Or did we make a mistake somewhere along the way? So the mistake that we made was we needed values for these guys, right? Because they need to go, the states still need to update correctly. So what I want to do is go ahead and erase this. And let's come back here and let's figure out what those next states were going to be. Right? So if we have, so we started with x equals 0 and A and B were equal to 0. So x is equal to 0. So we have 0. Basically 0 is everywhere, right? 0, 0, 0, which means we had a 0 here and a 0 here. This is why everyone prefers to work with D flip-flops, because they're not nearly as confusing. All right. So now let's unpack. So A plus is equal to JA and A prime. So JA is equal to 0. A prime is equal to 1. Or KA prime is equal to 0, which means KA is equal to 0. KA prime is equal to 1. And A is equal to 0. So that means it's equal to 0. And then B is going to be probably about the same thing. In fact, it is going to be exactly the same thing. It's also going to be equal to 0, right? So JB is 0, KB prime, so B prime is 1, KB prime is 1, but B is 0, gets us 0. So we have zeros here, which means that for that next step there, everything kind of dumps into the present state. So that's going to be 0 and 0. Remember, these guys are always going to jump over. And now we can figure out what our output is going to be. So what do we have? X's are equal to 1s. So 0, 0, 0. A and B are both 0, so that gives us a 1, a 0, a 1, and a 0. So that gives us a 1, a 0, and a 0, which means that Z is equal to 1. All right. So there we go. So we went roundabout a little ways, and I apologize. I kind of got myself a little bit confused and had to kind of work it out a little bit here in real time. But is everyone sort of on board with where we're at now? The mistake we made is we needed to have calculated what the next state was right off the bat based on our initial conditions. And we didn't do that, and that kind of freaked me out a little bit, and I couldn't remember how to figure out what A and B were because I hadn't given them to myself. There was no way to calculate A and B because we hadn't determined our next state from the initial conditions. So Joshua says, so the first step is to set both outputs of the flip-flops and the inputs to 0. Yes. Yeah, so you need to set that guy equal to 0 and all of these guys equal to 0. And the important thing, the thing that we didn't do, and it led us to some confusion, or led me to some confusion, is you need to then figure out what these guys are. Don't leave them blank. Because you need these guys, these A plus and B plus, to set your A and B. So your A and B gets set from whatever the previous A plus B plus was. And then the thing that makes it different is you're going to add a different input based on your input sequence. So now from here, we can sort of chug through the rest of our stuff. So let me clean this up just a little bit. All right. Okay. So now we're here at x equals 0. So now we know. So our A and B are going to be primed directly off of A plus and B plus. So that's going to be 0 and 1. Now we have all the information we need to figure out Z. So if x is 0, that's going to be 0, 0, and 1. And A is 0, so that's going to be a 0 there and a 1 there. And B is 1, so that's going to be 0 and 1, which means we're going to have 0, 0, 1, which means that Z is going to be equal to 1. Now we can figure out our A plus and B plus. So x is 0, so that's going to be a 0, a 0, a 0, and a 0, which means that JA and KB are both going to be equal to 0. But now we can figure out our A plus. JA is equal to 0, so we have 0, and A prime, so A is equal to 0, so A prime is equal to 1, or KA is equal to 0, so KA prime is equal to 1, and A is equal to 0, which means we're still here at 0 for A. Now B is going to be, let's see, so JB is equal to 0. B prime is equal to 0 because that's equal to 1. KB prime is equal to 1. And B is equal to 1. It means that B plus is equal to 1. So we actually get the same state again, despite the fact that we toggled. All right. So next up, let's do the next level. We can kind of speed things up a little bit. All right, boom, 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 boom. Clear it out, clear it out, clear it out. Now we can actually leave all of this to be exactly the same because, oh, well, no, we can't. I lied. I tell lies, man. Give me the eraser. PowerPoint, all right. Because it's not quite the same. All right. So now we've got x equals 1. A and B you're going to take from the previous state, so 0 and 1. Now we can set up our z, so x is 1, gives us 1, 1, 0. A is 0, so that's going to be 0 and a 1. And B is 1, so that's going to get us a 0 and a 1. So that means we've got 0, 0, and 0 gives us a z equals 0. So even though the state isn't changing, the output is changing. So looking at A plus, oh wait, so we gotta set this up. So x is equal to 1, so that's gonna be 1, 1, 1, 1. A is 0, so KB is gonna be 0. B is 1, so JA is gonna be 1. So JA is 1. A prime is 1 because A is 0. So that means A plus is gonna be 1. We don't even need to look at the second term since it's OR. Now B plus is JB is 1, and B prime is 0, or KB prime is 1, and B is 1. So they're both going to be equal to 1. So A plus is 1, B plus is 1, and we're ready to move to the next step. All right. So let's see. I always forget to move my arrow. Now we've got x equals 0. A plus and B plus are going to dump over into AB, so AB get us 1 and 1. So now we've got x equals 0, so we've got 0, 0, 1. We'll also go ahead and put x's down here for 0, 0, 0, 0. Means JA and KB are also going to be equal to 0. Doesn't matter what A and B are, since it's an AND gate with 0. And then A and B are both 1, so that's going to be a 0, 1, 0, 1. So that's going to be a 0, 0, 0. Coming to Z, so Z is going to be equal to 0. Now let's see, A plus is equal to JA, which is 0. And A prime, which is also going to be 0. Or KA prime, which is going to be equal to 1. And A, which is also equal to 1. So that's going to give us a 1 there. And then B prime is going to be exactly the same, I think. JB is 0, B prime is 0, KB prime is 1, and B is 1. Gets us a 1 there. So we're going to have a 1 and a 1 for our A plus B plus. And now we're ready to do the last step, the last bit of the sequence. Just like so. And let's see, so our A plus and B plus dump over. X is equal to 1, so that's going to give us, it's all 1s again, so that's going to be 1, 0, 1, 1, 0, 0, 1. It's going to give us 0, 1, 0, which gives us a 0, or excuse me, a 1 at Z. And then looking at, so let's see, X is 1, so it's going to be 1, 1, so it's 1s everywhere. So A plus is going to be JA, which is, those are going to be 1, so that's going to be 1. And A prime is going to be 0. Or KB, or KA prime is going to be 0. And A is 1. So that means that it's going to be equal to 0. So the last next state for A is going to be 0. B plus is going to be exactly the same, 1, 0, or 0, 1. It's going to give us 0. So we're going to have a 0, 0 right there. And that is the end of our sequence. 1, 1, 0, 0, 1. Any questions about how we worked through that? Cool. Well, in that case, we're done pretty well in advance, man. That's actually all I've got for you guys today. We'll sort of wrap this up with kind of a last look at the behavior of sequential circuits on Wednesday, and then we'll prep for the third midterm, and then we'll prep for the final exam. So almost done. So if there are no more questions, comments, concerns, then I'll see you guys on Wednesday. Don't forget, I've got my office hours from 3 to 5 today. I know you have an assignment due. Seriously, my office hours are not really supposed to be a tutoring session. I'm obviously available for that, but go to Aria first. She's the tutor. She's geared up for it, and she is available today. So I would recommend go there first. And if Aria can't help you, then come talk to me, but go to Aria first. But I will still be available from 3 to 5 today. So if there's nothing else, thank you so much, guys. I'll see you on Wednesday.